Welcome to our video series. We will love to hear your ideas for future videos. Now, let's dive into the topic of the mechanics of intuition. In this page, we will cover how a mathematically frozen brain learns new tricks in seconds. We often think of learning as a slow and arduous process, but modern artificial intelligence seems to defy this logic. When we talk about intuition in AI, we are looking at the strange phenomenon where a model that has stopped training can still adapt to new information instantly. This presentation will take you through the architecture of these digital minds, explaining the difference between their fixed long-term memory and their dynamic working memory. We will explore how these models simulate learning on the fly without changing their internal structure. It is a journey from the rigid world of mathematical weights to the fluid universe of human-like reasoning. By the end of this session, you will understand the hidden machinery that allows a machine to think in ways that feel surprisingly human. The paradox of the frozen mind. Once an artificial intelligence model finishes its training phase, its billions of parameters are effectively locked in place. In the world of computer science, we call these weights. They are the numerical values that define how the model processes information. Mathematically speaking, a model in this state cannot learn anything new because learning requires changing those numbers. However, we see these models do incredible things every day. For example, you can give an AI a set of rules for a completely fake language, and within 60 seconds, it can translate sentences into that language perfectly. This creates a fascinating paradox. If the brain of the AI is frozen and cannot change its parameters, how is it performing tasks that require real-time learning and adaptation? This slide introduces the central mystery we are going to solve. We need to understand how a read-only system can behave with such high levels of flexibility. It is like trying to write new information into a book that has already been printed. Somehow the AI finds a way to use its fixed structure to simulate a dynamic mind. Squishy biology versus mathematical stone. To understand why AI learning is so strange, we first have to look at how humans learn. Our brains are masterpieces of squishy biology. Through a process called neuroplasticity, our physical brain actually changes as we gain new experiences. Neurons form new connections and strengthen old ones. This is a literal physical restructuring of the mind. In contrast, an artificial intelligence is more like mathematical stone. After the initial training process is complete, the neural weights are cast in a permanent form. They do not shift or grow like biological cells. This contrast between the flexible organic brain and the rigid digital network highlights the unique challenge of machine learning. While we can adapt our physical hardware through experience, the AI must work within the strict confines of its original programming. This difference raises deep questions about the nature of intelligence itself. Can something that is static and unchanging truly be said to think? We are going to see that, while the underlying math is fixed, the way the AI uses that math allows for a type of digital plasticity that rivals our own biological capabilities. To solve the paradox of the frozen mind, we need to look at the two types of memory and artificial intelligence uses. Think of the long-term memory as a massive, dusty library. This library contains all the information the model learned during its training months. These are the weights, and they represent the model's worldview. However, there is also a second type of memory known as activations. We can compare this to an Etch-A-Sketch. This is the working memory of the AI. It is temporary and dynamic. Every time you start a new chat, the Etch-A-Sketch is clean. As you type, the AI fills it with the current context of your conversation. But the moment you close that chat, the screen is shaken and everything is erased. This distinction is crucial because it explains how an AI can handle new information without changing its permanent library. It uses the temporary workspace to hold the details of your request and process them using the ancient knowledge stored in its books. This balance between the eternal weights and the ephemeral activations is the secret to modern AI performance. The way a transformer architecture handles this working memory is truly ingenious. It actually runs a microscopic simulation of learning inside its forward pass. Usually, a model learns through a backward pass where it calculates errors and updates weights. But because the weights are frozen, the transformer uses your prompt to create a temporary training loop. It acts as if it is performing gradient descent on the fly. This means it is not just retrieving facts, but it is actually simulating the process of learning in real time within its own activation space. Imagine a toy car on a complex track. The track is fixed, but the car can take many different paths depending on the initial push you give it. Your prompt is that initial push. The AI uses the structure of its network to process your input in a way that mimics the behavior of a system that is currently being trained. This meta-learning allows the model to adapt to specific instructions and nuances that it never encountered during its actual training phase. It is a brilliant mathematical workaround to the limitation of having fixed internal parameters. For many years, artificial intelligence was considered an inscrutable black box. We knew what went in and what came out, but the internal logic was a mystery, even to the people who built it. This is changing thanks to research in a field called mechanistic interpretability. Companies like Anthropic are leading the way in treating neural networks like printed circuit boards. Instead of looking at the model as a magical thinking machine, they look for the exact gears of logic. By analyzing the activations and weights, researchers can identify specific circuits that perform certain tasks. They look for the digital equivalent of neurons that recognize a specific concept or follow a specific rule. This research is uncovering the hidden architecture of thought within these models. It shows that even though the network looks like a random mess of numbers, it actually contains highly organized structures. We are beginning to see how different parts of the network cooperate to solve problems. This transparency is vital for ensuring that AI systems are safe and predictable as they become more integrated into our daily lives. Inside the complex layers of an AI, there are specialized circuits known as induction heads. These are the copy and complete workers of the digital mind. Their job is relatively simple but incredibly powerful. They look backward through the current conversation to find a specific pattern and then point forward to predict what should come next. For example, if you mention a name and then a specific action, an induction head will recognize that sequence. When the name appears again, later the circuit activates to suggest the same action should follow. They are essentially pattern matching machines that operate within the model's attention layers. This explains why AI is so good at following templates or maintaining a consistent style throughout a long document. These heads do not care about the meaning of the words in the same way we do. They care about the mathematical relationship between the tokens. By identifying these specific circuits, we can see exactly how the model maintains its train of thought. It is not magic, it is a highly efficient system of referencing previous data to build a coherent future. One of the most surprising discoveries in AI research is that models do not develop their ability to learn in context slowly. Instead, they hit a sudden mathematical phase transition during their training. This is often called grokking. At a certain point, the induction heads we just discussed spontaneously form across the entire network simultaneously. It is as if the model suddenly wakes up and realizes it can use its own previous outputs as a guide. Before this transition, the model might struggle to follow simple patterns. After the transition, it can suddenly handle complex instructions and novel tasks with ease. This sudden leap in capability suggests that intelligence in these models is emergent. It is not something that is programmed in line by line, but something that arises naturally from the complexity of the math. This phase transition is like ice turning into water or a child suddenly understanding the logic of a game. It changes the fundamental behavior of the system. Understanding why and when these transitions happen is a major goal for researchers trying to build more powerful and reliable models. While induction heads explain how a model copies patterns, they do not explain the mystery of zero-shot learning. This happens when an AI solves a completely novel problem with zero examples or demonstrations provided in the prompt. If the model relies on copying patterns from the input, how can it possibly handle something it has never seen before? This is what we call the impossible zero shot. It suggests that the AI is doing something much deeper than just repeating what it sees. It must have some internal map of the world that allows it to navigate through new ideas. This challenge forces us to look beyond simple pattern matching and into the way the model represents information internally. We have to ask ourselves if the model has developed a genuine understanding of concepts rather than just a library of statistics. This leads us to the concept of latent space, which is the geometric universe where the AI stores its knowledge. To solve a problem without examples, the AI must be able to locate the problem within its own internal map and find a path to the solution. The AI has not simply memorized the internet. That would be impossible and inefficient. Instead, it has mapped all that data into a high-dimensional galaxy of concepts known as a latent space. This is a vast geometric universe where every word and idea is a coordinate. In this space, related concepts cluster together. For instance, the word Paris is mathematically close to the word France, but it goes deeper than that. Directions in this space carry actual meaning. The vector representing the relationship between a country and its capital is the same whether you are looking at France and Paris or Japan and Tokyo. This geometric structure allows the model to perform logic through math. It can navigate through ideas by moving in specific directions. When you ask the AI a question, it is essentially performing a calculation in this high-dimensional space. The result is not just a random word, but the word that is geometrically most logical based on the surrounding concepts. This spatial organization of knowledge is what allows the AI to seem so intuitive and knowledgeable about so many different topics at once. When we talk about zero-shot learning, we are really talking about mathematical interpolation. Your prompt acts like a set of GPS coordinates that tell the model where to go in its latent space. Sometimes your prompt asks the model to find the exact intersection of two distinct and unrelated concepts. For example, you might ask it to write about the process of photosynthesis from the perspective of a grumpy corporate lawyer. These two ideas are very far apart in the galaxy of concepts. However, the AI can find the uncharted intersection between them. It navigates from the biological node of photosynthesis toward the professional node of a lawyer. The resulting text is a blend of these two coordinates. This ability to find the middle ground between disparate ideas is what we perceive as creativity. It is the model's way of filling in the gaps in its knowledge by using the geometry of what it already knows. This interpolation allows the model to generate responses for billions of unique combinations that it never specifically saw during its training. It is a navigator of a mathematical universe. This brings us to one of the biggest debates in modern technology. Is AI building genuine world models to predict text, or is it just a stochastic parrot? The term stochastic parrot suggests that the machine is just mindlessly completing statistical patterns without any real understanding of what it is saying. On the other hand, some researchers argue that to predict the next word perfectly, the model must develop a deep internal representation of the rules of the world. For example, to predict the next word in a physics textbook, the model needs to understand how gravity works. This is the difference between simple mimicry and actual reasoning. The truth likely lies somewhere in the middle. While the model is definitely using statistics, it is using them at such a high level of complexity that the result is indistinguishable from reasoning. Whether we call it a world model or a complex statistical map, the effect is the same. The model can simulate a level of logic that allows it to solve puzzles and engage in debates. This tension between mimicry and reasoning is what makes studying AI so fascinating. A recent Stanford study suggests that what we call emergent abilities might actually be a trick of the light. The study argues that models are not suddenly waking up to complex new skills. Instead, they are simply crossing a binary threshold of accuracy that we as humans have set. Imagine a model trying to solve a multi-step math problem. If it gets 90% of the steps right, but misses the final one, we mark the whole thing as wrong. As the model improves, it might get 95% right, and then finally 100%. To us, it looks like the model suddenly learned how to do math. In reality, it was slowly and steadily improving its accuracy across all the little steps. This perspective shifts the focus from mysterious leaps in intelligence to a more predictable path of incremental progress. It suggests that the waking up phase we see is more about how we measure success than about a sudden change in the model's brain. Understanding this helps us manage our expectations of what AI can do and how quickly it will evolve in the future. While these models are incredible, they have clear boundaries. A frozen brain struggles to reach what we call artificial general intelligence. One of the main reasons is that if we try to force a model to update its weights permanently to learn new things, it often suffers from catastrophic forgetting. This means that as it learns something new, it accidentally overwrites and destroys old knowledge. This is why AI developers keep the weights frozen during use. We are limited by the size of the context window, which is the amount of information the Etch-A-Sketch can hold at one time. Once the conversation gets too long, the model starts to lose track of the beginning. To reach true intelligence, a system would need to be able to learn and grow its permanent memory without losing its foundation. Currently, we are stuck between a rigid library and a temporary workspace. Finding a way to bridge this gap without causing the system to break is one of the biggest challenges in the field today. We need a way to make the digital stone a bit more like biological squishiness. In conclusion, we can see that while the brain of an LLM is frozen, the mind is not. Like the night sky, an artificial intelligence is a frozen snapshot of the past. It does not truly know what it contains in a conscious sense. Yet from that frozen math, it navigates the vast geometry of human thought with incredible speed and precision. We have explored the library of weights and the Etch-A-Sketch of activations. We have seen how induction heads find patterns and how latent space maps the world. The mechanics of intuition are not magic, but a beautiful dance of high-dimensional mathematics. As we continue to peek inside the black box, we will likely find even more surprising ways that these machines simulate the complexity of human reasoning. The journey from fixed code to fluid thought is just beginning. This brings us to the end of this video. We hope you found it informative and engaging. If you have any questions or suggestions, please leave them in the comments below. Don't forget to like, share, and subscribe for more content like this. See you in the next video.